Alright, so for example number 2 here, we need to determine the exponential function given this graph. And so to start off, my always key point here is always start off with what you know. So know that our graph should be in the form of y is equal to c of x. So you don't know where to start there. You know that exponential functions will be in the form y is equal to c of x, and that's, or I guess mostly just for this section. Next section we'll be looking at some translations which will have a different form, but just for today we're working with y is equal to c of x. And if you guys think back, how would you normally do this? Say if you had a linear equation or a quadratic equation. Normally you pull some points from this graph, the graph that you were given, and then plug it in and then find those missing values. And that's exactly what we're going to do here. Okay? So we're going to pick really nice easy values, and I'm going to give you a hint, and you're going to do this with all of the exponential graphs that we'll be working with today. So here we're going to be, let's pick a point, and your easiest one here is always 1 and 2, or so we'll pull that value there. This one we're given from the graph here. And I'm going to give you a hint. You're always going to want to choose where x is equal to 1. And why do you think I would do that? Let's put this in. Y is equal to c to the power of x, and we're going to have x is equal to 1. What do you notice about c to the power of 1? Anything to the power of 1 is just a number itself. That means that your c value is equal to y. So you typically don't want to go with, say, here we're looking at the graph. If we chose 2 and 4, we're going to have to do some work. We don't want to do work. Come on, let's face it. We want this to be nice and easy. Let's pick some easy values. That's why we're going to go with where x is equal to 1. Okay? So then what can we say about c? C is then equal to that y value, and so c there is equal to 2. Right? So now that we know that c is equal to 2, now let's rewrite this as our exponential function. So we have y is equal to c, which was 2, to the power of x. Okay? So not so bad. Find out where x is equal to 1, and c then, using that, we know that an exponent of 1 will be that whatever number is the base. So then c is equal to y. That's basically essentially no work. It's easy. You know, life is good, all right? But one thing we do want to do, let's make sure that this is right. So let's verify this. And sorry, I'm just going to do this over here on the right or left-hand side here. So let's verify. If you guys remember, how do we verify? Well, choose another point on that graph there and see if it works. And you know what? Since we've got this one already circled here, let's go with 2 and 4. And if I could offer you guys, why can't I choose 0 and 1? So one thing I'll say is that if you guys remember, in any standard function y is equal to c of x, no matter what your value of c is, your point is always going to be at 0 and 1, that y-intercept there. So that point exists for every single function or exponential function that is out in the form of y is equal to c of x. So never choose 0 and 1, because then it would work no matter, even if you made a mistake, it would still work. So pick one that is somewhere on that graph that is not 0 and 1. Okay, so here we have 2 and 4. So here we have y is equal to 2 to the power of x. 4 is equal to 2 to the power of 2. And 4 is equal to, if you guys know 2 squared, that is simply just 4. So that works. Alright, so just quick repeat. So when you're starting off, you start off with what you know. You know that any exponential form, essentially as long as there's been no translations, which we'll deal about next section, so don't even worry about it. Start off with this form. You know that y is equal to c to the power of x. Then from there, find out where x is equal to 1, because then you'll find that c is equal to y where x is equal to 1. Then fill in your values, and there you go. Write it as your exponential function there, and we're good to go. Okay? So now let's move on to number 3. So we're going to do another example so you guys will have lots of practice, And if I can mention one thing here, ladies, that I had some of this graph got cut off, and I need to fix it up a little bit. So here we need to change our x-axis. Let's add in values. So we have time here is your x-axis. That is in decades there. And our y-axis is values in dollars. And because we're only dealing with time, we're not even going to be bothering with this negative stuff here. So we're just going to be looking at this nice little large area of the graph that I gave you guys. You're welcome. All right. So just now that I got that nicely done and over with, so question number 3 here says that Tia has just graduated from university and wants to begin her retirement planning. Her investment advisor suggests an investment that he expects to double in value every decade. So when we're saying double in every decade, right there, that's kind of a key word. We're dealing with exponential functions. So the estimated growth rate is modeled by the exponential graph shown below. So in A here, we need to state the domain and the range of the function and then explain the significance of the y-intercept, okay? So I'm going to scroll down here so we have lots of room there. I have faith that you guys can read that on your own piece of paper. Okay, so for A here, we need to determine the domain. And that, if you guys look there, we have x such that, and we really shouldn't have this back here. We're dealing with time. So what we're going to be looking at here is that x must be greater than or equal to 0, where x is an element of all real numbers. So once again, I'll apologize for that wonderful graph that I gave you. Oh boy. Alright. And our range there is at y such that y must be greater than 0, where y is an element of all real numbers. If this wasn't a word problem, we'd probably have the same restrictions as every other kind of graph that we've looked at, but this one's a word problem. We know that our values, well, hopefully we wouldn't be in the negatives, because then now we would owe, especially since we're doing investments. But definitely not time. We don't go back in time. That is not possible, or at least just yet. That'd be really cool if it did, but as it is, not yet. Okay, so now to finish off part A, we need to talk about what does the y-intercept mean. So if you guys look here, your y-intercept there is at 0 and 1. Big surprise there, right? Big surprise. Alright, so what does that mean when your x value, your time is at 0, and your y value, or your values in dollars, is 1? So essentially what that there is saying is that at time 0, or when you initially invest, so at the beginning, the value of each dollar is 1. Oh, alright, so essentially when you first put it in, you put in $1, and if you want to take that out immediately, you're still sitting at $1. So for every dollar you invested, you're still sitting at $1, okay? Alright, so for B there, we need to find the exponential function that represents this graph. And what we can say here is that, remember, our general form here, we have y is equal to c to the power of x. Then, simply all that we have to do is we have to find where x is equal to 1 on the graph. And there you guys know that, or if you guys can see that, it is at 1 and 2 there. So that means that our c value there is where y, so that means that c is equal to 2. So we can rewrite that as y is equal to 2 to the power of x. Okay, so we kind of saw that trick from the last question. Hopefully we still remember that. Alright, so that is our exponential function there. And so now we'll move on to C there. So C is asking what is the value of $1 invested for 10 years. So that is when x is equal to 10. You guys can use your graph, or if you guys want to be a little bit more, I guess, more accurate, let's put this into our equation. So we have y is equal to 2 to the power of 10. If you guys put that into your calculator, you will find that your value there is y is equal to 1,024, and we're dealing with dollars there. So for $1, your value will be after 10 decades. And just remember, 10 decades, that's a long time. That's like 100 years. That is that $1 will be $1,024. All right. So just to make one point here, I'm gonna quickly erase this. So make sure you guys get this written down. I'm gonna quickly pause this and erase all the information so we have room for D and E. All right. So for D here, that question there is asking how long will it take for $1 in this investment to be worth $8? So what we want to know here is at what time will our y value, so be the value in dollars, When will that be 8? So you can either use your graph, or you can double check this. You know, this is a good way to also verify your equations. So you have y is equal to 2 to the power of x. We're given y in this equation, so we know that 8 is equal to 2 to the power of x. There's two different ways you guys can solve this. If you already know that 2 to the, say, the power of 3 is 8, that is absolutely fine. Or what we can do here is we can rewrite 8 as an exponent of 2. So we have 2 to the power of 3 is equal to 2 to the x. Then your exponents have to be the same. So you know that x is equal to 3. So that's using your exponential rules, or that's what you guys learned in pre-calculus 20. So hopefully you guys remember that there. And then one thing that we can do there is double check it using your graph. So we're going to go find x is equal to 3. Then you're going to go all the way up until we get to right there. So there we can see that when x is equal to 3, y there is equal to 8. So that means after 3 decades, your dollar will be, $1 will be worth $8. That's pretty cool. So after 3 decades or 30 years. Okay, and I guess if you guys want to write the units there, we're in x is equal to 3 decades. So now moving on to E. Here we need to use the table of values to determine how long it will take for $1 in this investment to be worth $26. So here what we're basically going to do is we're going to create a table of values, and we're just going to basically do some trial and error, okay? So we're going to start off with our x and our y, create your table of values, and essentially we're just going to play around with some values. And what we can do is we can use our graph, and if you guys see, when we get to about, say at x is equal to 4, we're at all the way up to 16 there. If we move 1 over, we can't even see that graph over at 5. So we're going to have to play around a little bit, but we can really exclude, obviously we can't have 4 or less. That obviously cannot work, but so it might be, maybe we could take a guess that it might be between 4 and 5. So if you guys want to, maybe I'll first start off with, what is y when x is equal to 4? So here we have 2 to the power of 4. If you guys either know that off by hand, or if you guys put that to your calculators, you know that y will be equal to 16. So obviously we need to go up from there. So let's try what is y when we put x is at 5. So 2 to the power of 5 there. Here we're at 32. Okay, so now we've gone over, because remember we want to get to 26. So here we're looking for y is equal to 26. So now we might have to start going into some decimals, and this one you're definitely going to have to use your calculator for, unless if you guys can do this off by hand, but that's, you know, dealing decimals, yikes, that's crazy. Let's just use our calculators for that one. So next we can try, let's see what 4.5 is. This one, we'll go in the middle, see where it takes us, and from there we can either go up or down. So when we put 2 to the power of 4.5, that there is equal to 22.6. So put that into your calculators. You guys should find that it should round off to about 22.6. So obviously from there we need to go up. So it's got to be between 4.5 and 5. So our next one, if you guys want to try, let's try 4.7. Sure. It's kind of nicely in between those values there. Let's see what happens when we put 4.7 in for 2. So we have 2 to the power of 4.7. Put that into your calculators. And what you guys will find is that we are at 25.99. So that there is actually pretty darn close. I would expect you guys to go into more decimals. If you guys want to try 4.8, but you find that that's too high. So what we can say is that approximately, after approximately 4.7 decades, or 47 years, the value of $1, you can say $1 invested in the investment will be $26. Okay, and then that's it. That's all. We've answered all the questions, and so you guys can get started on your homework.